Chapter 7 of The World's Lumber Room by Selina GAYE. This LibriVox recording is in the public domain. Chapter 7, Dust Makers, Vegetables and Animals. We have seen from the last chapter that a stream of lava continues intensely hot for a long time, and may emit vapour, and even go on creeping slowly down the mountainside for years after it has been poured forth. Long after it has ceased to move, and centuries after it has become perfectly cold and solid, the surface of the stream will remain fresh, smooth, and glossy, effectually resisting all attempts both of air and weather to convert it into dust, as we may see by the lava streams of Ascension Island. Even lava has to yield at last, however, and that to workmen whom we should at first sight be inclined to call very insignificant. Nothing more, indeed, to all appearance, than mere stains such as one sees upon a brick wall. These discolour the surface here and there, and upon examination with the microscope prove to be vegetables, of a very humble kind, it is true, but still vegetables, nature's gardeners and first soil makers, which will prepare the way for more important plants. Lichens, as they are called, are to be found everywhere. No climate, hot, cold, damp, or dry, and no soil seem to come amiss to them, for they will grow loose on the surface of the sand in Peru and attach themselves to the dry bones of mules which have died by the wayside. They are invariably the first plants to make their appearance, whether upon lava or upon the rocks of islands newly raised above the sea, and no rock is too hard for them. The multitudinous spores by which they are propagated are for ever floating in the air, and being furnished with a gummy fluid are able to attach themselves to the barest, smoothest surface, and when once they have gained a footing they are simply irresistible. They flourish on granite, slate, lava, and in Berkshire, Massachusetts, even the white quartz hills are covered on their moister slopes with large patches of a leathery lichen, which adheres so firmly that it can hardly be detached from the stone. The first lichens to appear are, as has been said, mere stains, but by the growth and decay of successive generations of these, a thin film of soil is formed, upon which larger kinds take root in their order, and at last one may see rocks or old tombstones covered with a crust of lichen an inch or more thick. On this crust mosses begin to grow, and they help on the process of decay by keeping the surface moist and sending their roots down into the stone. Then insects collect and feed, die and decay, and thus the mineral matter of the rock is not only reduced to powder, but mixed with organic remains, without which it would be quite unable to support the higher orders of plants. The mosses, as they grow thicker and thicker, keep the air from the rock, and thus to a certain extent protect it. On the other hand, they also keep the surface moist, and as moist surfaces absorb more carbonic acid than dry ones, this also helps forward the decay to some extent, even though the other enemy, frost, be kept out. Now, how do the lichens manage to wear away the rocks, since though low down in the scale they are certainly plants, and plants can live only upon liquid food? Yet these eat their way not only into bricks which have been baked, but into rocks which have been vitrified, converted, that is, into a sort of glass by the heat of the subterranean fires. On removing a lichen from the rock, we see that it has made an impression more or less deep, and that the stone has lost so much of its substance, and further, on burning the lichen, we find that it contains from 10 to 20% of solid ash, which will not burn away, being, in fact, mineral matter abstracted from the rock. How, then, has the lichen managed to feed upon stone? All plants have the power of forming within themselves acids of one sort or another, and as lichens do this to a larger extent than most others, they are able to dissolve the very hardest rocks. Many of them, indeed, so abound in oxalic acid that oxalate of lime makes up half their weight, and many of the old Greek marbles are thickly encrusted with this substance from the growth and decay of lichens on their surface. Oxalate of lime is simply a combination of oxalic acid and lime, the acid having dissolved the lime from the rock or marble, and so brought it into a condition in which the lichen could absorb it. But though lichens are the first soil makers and take up more mineral matter in proportion to their size than any others, still all plants contain some acid, and all, on being burnt, yield a certain quantity of ash, some more, some less, which they have absorbed from the soil, and could not have done except in the form of liquid. We have already seen something of the solvent powers of carbonic acid, and this gas plants are constantly giving off through their roots, which are much more numerous than people generally have any idea of. Rye, beans, and peas, for instance, will send down a thick mat of white fibres to a depth of 4 feet. Winter wheat has been known to send out roots 7 feet long in 47 days, while clover, a year old, has roots 3 feet and a half long. But this is not all. Besides these obvious roots, there are very many others so fine and hair-like that they escape notice altogether. Yet the plant takes up its nourishment through all, and especially through these young, almost invisible roots. By way of experiment, beans, maize, and wheat have been planted in fine quartz sand, having at the bottom plates of marble, carbonate of lime, magnesian limestone, carbonate of lime and magnesia, gypsum, sulphate of lime, and glass. Being kept well watered, the seeds soon began to sprout and send out roots, and when they had reached the plates below and could get no farther, they spread themselves out horizontally. When the plates were examined after a time, the marble and magnesian limestone were found to be corroded, eaten into, by the roots, the impression of even the root hairs being distinctly visible. No effect seemed to have been produced on the glass or gypsum, but that, after all, might only mean that it was as yet too slight to be perceptible. Smooth pieces of limestone are often found in meadows with their surfaces covered by a perfect network of small furrows, which on careful examination are seen to correspond exactly with some tiny root or rootlet. Lupins are especially active in decomposing mineral matter, and for this reason they are sometimes, as in the Azores, planted with corn and ploughed in as manure. 3 lupins planted in powdered sandstone have been found to take up 3/5 of a grain of mineral matter. An equal number planted in powdered basalt took up 3/4 of a grain. 3 peas took up rather less basalt and much less sandstone, and buckwheat, vetches, wheat, and rye considerably less of both, but all showed a marked preference for the basalt. Their work did not, however, end with what they had absorbed, for it was found that they had dissolved more than they had used, and the soil was therefore so much the better fitted for the support of other plants. All plants require sulphur, phosphorus, flint, iron, potash, soda, lime, magnesia, and chlorine for their proper development, and though they may take but an infinitesimal amount of some of these, all are equally necessary, and the absence of any one would prove fatal. Some take more of one and some more of another, and even the different parts of the same plant may take the minerals in different proportions. Thus grasses and all the varieties of corn take up much more flint than turnips and cabbages do. And while the ash of horse chestnut bark contains 12% of potash and 76 of lime, the ash of the wood yields twice as much potash, that of the leaf stem nearly 4 times as much, and that of the flower 61% of potash and 13 of lime. All the cresses, on the other hand, contain a large proportion of sulphur, and though a crop of mustard may be grown on damp flannel, it is not to be supposed that it lives and flourishes on air and water only, for the water, unless it be distilled, is quite certain to contain some mineral matter, and from this source the plants derive sufficient food for a time. If grown in pure water they will sprout and even grow at first, but as soon as they have used up the matter contained in the seeds they will die. And if they be burnt, the remaining ash, when weighed, will be found to be only the same in amount as that contained in an equal number of seeds, showing that they have not been able to find anything in the water. Every crop, therefore, takes a certain amount of mineral matter from the soil, and as one takes more of one thing and another more of another, the farmer varies his crops that the soil may not be exhausted. Footnote: in general, probably 99% of the soil without water does not contribute to the support of vegetation. The hay crop takes up the largest amount of mineral matter, but reckoning it at 2½ tons to the acre, it takes only 400 pounds. The weight of the soil, 1 foot deep, is 4,000,000 pounds per acre. S. W. Johnson. End of footnote. Sometimes he will let it lie fallow altogether, that the carbonic acid and ammonia washed down by the rain may dissolve the minerals and prepare them for plant food, and the same end may be more quickly attained by the growing and ploughing in of green crops. But of course neither plan will answer unless the minerals are already in the soil, and if they are absent, the farmer himself must supply them in the shape of bones, ashes, etc. Many grasses, especially the stiff, harsh kinds, and all varieties of corn, contain much silica or flint. What they want it for is not clear, for it does not seem needed to give strength to their stems, as has been supposed, but they cannot do without it. In barley straw more than half the ash is flint, in winter wheat 41%, in meadow hay 29%. Footnote: the proportion of ash of all sorts, though not invariable, is about as follows: field beet 18.2%, red clover 6.7%, wheat straw 5.4%, wheat grain 2%, pea straw 7.9%, pea grain 2.7%, fir bark 2%, fir wood 0.3%. End of footnote. Among trees, while the willow and oak contain very little flint but a great deal of lime, the Scotch fir takes as much lime as the willow and 21 times as much flint, and the cortoad tree of South America has bark as hard as soft sandstone from the quantity of flint it contains, and the natives of Trinidad use its ashes in place of sand, with the clay of which they make their pottery. The smooth, glossy rind of the bamboo, which contains 70% of flint, will strike fire with steel, and the same substance collects in hard lumps like opal in the joints of the stem. There is flint again in the hairs of the nettle, in hemp, and in hops, and all the best vegetable weaving fabrics, except cotton, contain a great deal. Of all our native plants, however, none contain more than the horsetails, formerly used for polishing by cabinet makers and metal workers, and still made use of in some parts of the country for scouring pots and pans. Half of their ashes, and in some varieties more than half, consists of flint, so that they are a sort of natural sandpaper, and were at one time largely imported under the name of Dutch rushes. If examined through a microscope, their cells, regularly arranged lengthwise in ridges, may be seen encrusted with silica, and if the whole plant be placed in nitric acid, all the soft parts will be eaten away, while the flinty skeleton will remain entire. Living structures, whether animal or vegetable, possess extraordinary powers of acting on mineral matter, and a humble lichen will produce more effect on a piece of rock with the sulphuric, oxalic, or nitric acid it contains then an equal amount of acid would do if otherwise applied. Nor would a dead lichen, however acid, be able to do what a living one does. What is true in this respect of lichens is true in their degree of all plants. And when we consider to what a depth many roots must penetrate, and that wherever they go they effect some chemical change, we can readily understand that as dust makers they are too important to be passed over. Moreover, the chemical effects of vegetation are not all that is to be thought of. The mechanical effects must also be taken into account. Few plants are more fragile and delicate looking than a maidenhair fern, yet one knows that its roots are strong enough to crack the pot if they have not room enough. Weighty curbstones have been seen to be forced completely out of place by the tender blades of grass growing between them, and Canon Kingsley mentions having seen a large flat stone raised up in a single night by the growth of a crop of tiny mushrooms. Then again we read of a nut tree springing up in the centre hole of a disused millstone, whose stem grew and increased in size until it entirely filled the hole, whereupon it gradually raised the stone from the ground until the huge mass, some 5 or 6 feet in diameter, was lifted up 8 inches all round, and was supported in the air by the stem only. The tree attained the height of 25 feet, bore excellent fruit, and was killed at last, not by the weight of the stone, but by the tightness of its embrace, which stopped the flow of sap. This is certainly a striking example of the tremendous powers of nature. And since trees and plants grow as vigorously downwards as upwards, their roots must certainly help to break up the rock, not only by causing decomposition, but by forcing their way into joints and cracks, and then gradually widening them. The island of Aldabra, northwest of Madagascar, for instance, is being reduced and destroyed by the silent inroads of the mangroves, which grow along the base of the cliffs and have eaten their way into the rock in so many directions that the island is completely riddled by creeks of their making. But we must now pass on to more intelligent burrowers, foremost among whom comes the great army of worms. It has been calculated that there are as many as 53,767 worms in each acre of garden ground, and about half that number in cornfields. 9 burrows, and sometimes many more, are usually found in 2 square feet of garden soil. And it is computed that all over the 32 million acres of cultivated land in which worms are able to live in Great Britain, 10 tons of earth are brought to the surface in each acre by the worms alone every year. Moreover, various acids called humic are generated by the digestion as well as decay of the vegetable matter which forms so large a part of their food. And as these seem to be even more powerful than carbonic acid, they must play an important part in the disintegration of the rocks. Worm burrows being frequently 5 or 6 feet long and even longer, some small amount of acid at least must be carried down to these depths, there to act upon the underlying rock or fragments of rock, and as all the mould is in constant though slow movement, fresh surfaces must be continually exposed to the action both of the humic acids and the carbonic acid of the soil. The green streaks sometimes seen in red marls or sandstone are caused by the decay of vegetable matter. Footnote: marls are a mixture of lime and clay with little or no sand. End of footnote. Humic acids have been formed, and these have robbed the red oxide of iron, to which the marl owes its colour, of some of its oxygen, leaving it green or bluish green. And as worms drag enormous quantities of leaves into the ground as linings for their burrows, as well as for food, they must greatly promote the formation of these powerful acids. Worms also frequently undermine and even penetrate the walls of old buildings, and by thus causing them to sink, have by degrees helped to bury them. No building is safe from their burrowing, it is said, unless its foundations be carried down to a depth of 6 or 7 feet. Worms are found in all moderately damp countries, and wherever they are they help to wear away the rocks and make dust, not only in the ways already mentioned, but also by swallowing a large amount of earth and even small stones, the latter of which are ground and reduced in size by the process of digestion, while the former is rendered so fine as to be more easily washed away by the rain. In some countries ants also do an amount of excavation which may well be called enormous, considering the size of the workers. At Rio de Janeiro, for instance, a species of the Sauba ant has made a tunnel under the bed of the river Paraíba, where it is as wide as the Thames at London Bridge. At the Magori rice mills near Pará, they once pierced the embankment of a large reservoir, and upon fumes of sulphur being blown down some of the main entrances to their colonies, the smoke was seen to issue from a great many outlets, one of which was 70 yards away. Among the larger burrowers may be mentioned rabbits, moles, marmots, sand martins, and other birds. In some parts of Tartary the rocks are perfectly riddled by the holes of marmots, and in South America there is a small bird called by the Spaniards casarita, or little householder, which makes a narrow cylindrical hole nearly 6 feet underground, at the bottom of which it builds its nest. The holes are made in any low bank of firm sandy soil by the side of a stream or road, but occasionally the birds make the mistake of choosing a mud wall, and at Bahia Blanca Mr. Darwin saw one which they had pierced in 20 places, to the great annoyance of its owner. The wall was a low one, and the birds were constantly flying over it, but had not the wit to see that it was not thick enough to suit their purpose. It has been already mentioned that roads paved with hard granite are quickly worn away by the constant passage of heavy traffic, but it would hardly be imagined that the passing to and fro of birds' feet could make any impression on the rocks. Yet in Nightingale Island, Tristan da Cunha, these are actually smoothed and polished by the continual tread of hundreds of penguins on their way to and from the sea. Footnote: the island is a mile square and is inhabited by about 400,000 penguins, whose rookeries cover a quarter of its area. End of footnote. No doubt the flinty skeletons of the microscopic plants called diatoms, which are always found in abundance in the mud about their nests, adhere to their feet and act as polishing powder. Beneath the penguin rookeries are the holes of the prions and petrels, which are bored in all directions, the round being honeycombed to such an extent that it often gives way when human beings venture upon it. And much the same may be said of the sandy flats about the Cape of Good Hope, only there the burrowers are moles, whose tunnels are so large as easily to admit the hand and arm. Footnote: in the Chilean Andes, the burrows of the little chinchilla are so numerous as considerably to increase the difficulty of travelling. End of footnote. The boring molluscs, too, must not be entirely passed over, as, although their shells are as thin as paper and as brittle as glass, they are able to pierce wood, limestone, clay, slate, and even sandstone to the depth of several inches, and thus frequently destroy the foundations of jetties, sea walls, etc., and ultimately cause their destruction. Plymouth breakwater, which is constructed of hard marble-like limestone, was so much injured by their ravages that it was found necessary to replace the blocks between high and low water mark by granite, against which they are powerless. Somewhat similar excavations are made by a species of land snail, but this is believed by Dr. Buckland to work with its rasp-like tongue, whereas the pholas seems to have no other tool than its papery shell. End of chapter 7.